All right, and we'll do our another universal gravitational question for grade 12 physics class. It's a question about putting together or relating Newton's law of gravitation and centripetal motion. That's how Kepler's third law came about. So we'll take a look at that again. It'll be similar to questions we did in class in terms of the mathematics. So orbital motions routinely used by astronomers to calculate masses. A ring of high velocity gas orbiting at approximately 3.4 times 10 to the 4 meters per second, distance of 25 light years from the center of the Milky Way, is considered to be evidence of a black hole. Calculate the mass of the black hole and then how many times greater than the sun's mass is it. If I remember my astronomy correctly, it should be about 1,000,000 times larger than the sun's mass. And this is something they do quite often, though, is they figure out how fast something is moving out there in space. And then if it's moving, there's got to be a large mass at the center of it. Let's see what this calculation works out to be. We're given speed and we're given distance, and we can use that universal gravitation centripetal force relationship to very relatively easily calculate this problem. But we can't work in light years. 25 light years is a unit of distance, and we got to put that into meters. Okay? So we got to do some conversions here. So 1 light year is the distance light travels in 1 year. Well, light travels 300 million times 10 to the 8 meters per second times 3,600 seconds in 1 hour times 24 hours in a day. And we'll be a little bit more precise. There's 365.25 days in 1 year. So let's crunch that through. So 1 light year is 3 times 10 to the 8 times 3,600 times 24 times 365.25. 9.47 times 10 to the 15 meters. So if you travel a distance of 1 light year, that is very far, and for us, astronomically, that is a stone's throw away. Pretty close. So that's 1 light year. So we're going to multiply that by 25, because it's 25 light years from the center of the galaxy. Times 25 meters per light year, so our units work out. So the orbital radius of this thing is 2.37 times 10 to the 17 meters. 17, not squiggly line. We're given orbital velocity. Back up to the top of the question, 3.4 times 10 to the 4 meters per second, so we don't have to change anything there. So we have meters for our orbital radius, meters per second for velocity. So I'm going to relate Newton's force of gravity, which we did in class, so I'll go through it a little more quicker. Is that right? Faster right now. G, m of this case of the gas, mass of the gas, times the mass of the black hole, supposedly, divided by the distance to that black hole to the gas squared. So Newton's law of universal gravitation has to equal centripetal force, so it's the mass of what's rotating around, and it's the gas, mass of the gas, its velocity squared over its orbital radius, or its distance from the center of the circle squared. Oh, sorry, not squared. There's not a square down there, just r. A little bit of simplifying. The mass of the gas divides out. The mass that's orbiting doesn't matter. And you could multiply both sides by r. That changes that exponent to a 1. That crosses out. Remember, when you cross something out, it is not replaced with a 0. It's replaced with a 1. So our formula we're working with is G, mass of the black hole, over r equals v squared. So rearranging the mass of the black hole we're trying to figure out is the orbital velocity squared times its orbital radius. Cross multiply that up. Divide both sides by a universal gravitational constant, G. Alright, so mass of the black hole, put our numbers in, equals 3.4 times 10 to the 4 squared What's your math here? Times, I forget that number, that's a big one. 2.37 times 10 to the 17. Divided by 6.672 times 10 to the negative 11. So if you know your exponents in math and how they work, this is going to be a really big number. All right, so 3.4 times 10 to the 4 squared times 2.37 times 10 to the 17 divided by 6.672 exponent negative 11. So the mass of this black hole is 4.1 times 10 to the 36 kilos. That's a lot of black hole. And that is our answer for A. B, how many kind of suns is that? Well, we just divide that answer. Mass of the black hole. Take that answer from above, 4.1 times 10 to the 36 kilograms. Divide that by how much mass the sun is, which is 1.99 times 10 to the 28 kilograms. Double check that number. Oh, 10 to the 30. I'm glad I double checked. That would have looked quite the fool. That was 30 kilograms. So divided by 1.99, exponent 30. So the mass of this black hole is 2.1 times 10 to the 6 solar masses times the mass of the sun. So I was right. On the order of 1 million. It's just on the order of 2 million. I don't know, I still got it.